So what is this atoms and the nuclei concern things basically? So in this atomic physics or the atoms in this one, we'll be basically dealing with an how the atoms are going to be behaving in the different structures. That is mostly the Bohr's orbit and all these things. Good evening, ma'am. So Bohr's orbit and all these things we'll be discussing over there. So whenever a charged particle is there, so according to this one, we know that according to the Bohr's models, we know that whenever there is an the voice sees blur. Okay. Let me 1 second, sir. Hello, now can you hear me please? Now? Is it okay? Right, sir. So coming to this atoms, the Thomson model and all these things are there. The Thomson model of the atom. So according to the Thomson model, the atom is considered as an homogeneous sphere. So first one is called as a Thomson model. Thomson model of the atom basically. So according to the Thomson, he considered it as an homogeneous sphere. Positive charges in which the electrons are the sufficient number are embedded, like plums or the seeds in an watermelon sort of a thing. So as in a watermelon thing, the electrons are embedded like the electrons will be there as if a seeds in an that is an in a watermelon conditions. So this is your first model, and this is the second model is going to be the Rutherford model. Everybody knows that one. Rutherford's model, that is the famous alpha ray scattering. So whenever an alpha rays are being passed through the alpha rays are being sent by a radioactive element onto a gold foil. So they get the deviation based upon that one. He told that there will be the centrally particle or centrally heavy positively charged particle will be your nucleus, and you are sending an alpha particle here. Okay, and this is the line passing through the nucleus, sir. And this distance is called as the closest distance of approach. Distance of approach means how close an alpha particle can come down to the nucleus. So that can be obtained by kinetic energy is equal to half mv square, and the potential energy of the system, that is 1 by 4 pi epsilon naught z e square, 2 into z e square. 2 is for the alpha particle by distance of r, where here r is called as your closest distance of approach. So that can be written as an ze square by pi epsilon naught into mv square. So, and this distance is called as an b, represented by the b, and b is called as an impact parameter. Impact parameter is the perpendicular distance. Impact parameter is the perpendicular distance between the line joining which is passing through the center of the nucleus and the path of the alpha particle. It is the perpendicular distance between the line joining the line which is passing through the center of the nucleus and the path of the alpha particle is called as your impact parameter. So impact parameter is equal to B is equal to 1 by 4 pi epsilon naught 2 into z e square by r square into this is cot of theta by 2. What is this theta is? This is the actual path of the alpha particle. This is the deviated path of the alpha particle. The angle between both of them is called as your theta, and this is called as impact parameter. So these are the two important relationships that can be asked in the examination regarding the Rutherford. And apart from this one, there is another one, number of alpha rays scattered is inversely proportional to the sine to the power of 4 theta by 2. This is another important relationship which can be used in the case of Rutherford's atom. Okay. Next was the proposed by the Bohr's postulate, the famous one. So there are certain assumptions regarding the Bohr's one. So that is electrons will be moving in a circular orbit around the nucleus. Okay, so next one, they conserve the angular momentum, where the angular momentum can be written as an NBR is equal to NH by 2 pi. So like this, there are based upon these certain assumptions, the Bohr's model has been proposed. So according to the Bohr's model, the basic thing what he has mentioned is there will be a centrally nucleus particle called as centrally mass particle called as a nucleus. Around this one, the electrons will be moving in a circular orbit like this. Electrons will be moving. Since electrons are moving in a circular orbit around the nucleus, whose number is going to be the Z into E, then force electrostatic force between the electron and the nucleus can be written as a that is 1 by 4 pi epsilon naught into Z E square by R square. Since it is moving in a circular, this should be equal to the centripetal force, which is mv square by R. So one of the R can be removed here. Now on solving this one, that is you are left with 1 by 4 pi epsilon naught into Z E square by R is equal to mv square from this one. Radius R is equal to. If I write this 1 by 4 pi epsilon naught as an k, I'm going for this one. 4 pi epsilon naught, I'm writing it as an k. So R is equal to k into Z E square by mv square. Now, according to Bohr's, the angular momentum of an electron is mvr, m into velocity into r, is equal to nh by 2 pi. Now, on substituting the value of the r here, you can get the value of the r as n, or this is mv into r is equal to k into z e square by m into velocity square is equal to nh by 2 pi. So these relations are actually the very, very important one. From this one, velocity of the nth orbit is equal to 2 pi k into z e square by nh. So most important thing we need to remember is velocity of the nth orbit is directly proportional to the z and inversely proportional to the n. Now on substituting this velocity in the r, that means r is equal to k into z e square by m into velocity square in the sense 2 pi k z e square by nh. This is the radius of the nth orbit on whole square. On solving this one, you will be getting the r, that is the radius of the nth orbit is proportional to the n square by z. So these are the very, very important relationships We need to remember because in the examination we cannot all the way solve these things. It takes certain time over there, right, sir? So we need to definitely have to remember those things. So as we have got the radius and we have got the velocity of the nth orbit, you can now go for the kinetic energy of the electron. Kinetic energy of the electron can be represented as an half m v n square velocity of the nth orbit square. So on that sense, kinetic energy of the nth orbit is proportional to the, this will be the z square by n square. Similarly, your potential energy Pe of electron revolving in a circular orbit is also proportional to the z square by n square, and the relation between the potential energy and kinetic energy is, potential energy is equal to the 2 times of kinetic energy but with the negative sign. So this relation between the potential and kinetic energy is only valid for bounded systems, in the sense you can apply this relation only in the gravitation or in the here in the Bohr's orbit. So in the other places you cannot use this relation. So total energy is also equal to the or proportional to the z square by n square. So this is the relation of the kinetic energies and the total energies and all these things. So next one, if I go for the angular momentum, then as we know that angular momentum is equal to mvr, or which is equal to the nh by 2 pi. So angular momentum, that means L is proportional to the n. It will be basically n proportional to the, that is nth orbit in this case. So now leave it. Coming to the frequency, as we have got the velocity. So angular frequency, nothing but omega n. We know that omega n is equal to Vn by Rn, as the linear velocity is equal to the omega into Rn. So this is proportional to the velocity is proportional to which relation, sir? Here velocity is going to be, as we have just written here, velocity is proportional to the z and inversely proportional to the n. Substitute there, proportional to the z by n, and radius is going to be directly proportional to n square by z. This will be the n square by z. So that means omega is proportional to the z square by n cube. And further, next one, omega n can also be written as n 2 pi into frequency fn. So from this one, frequency of the nth orbit is also proportional to the z square by n cube. And we know that time period of rotation t is inversely proportional to the fn. So that means they have to be directly proportional to the n cube by z square. ఈ రిలేషన్స్ అన్ని కావాలి నాన్న, తప్పదు. Next one, time period we have got, frequency we have got, electric current. If I go electric current I is equal to, for a given time period, this is E by T, and I is inversely proportional to the time period, means I is also proportional to the z square by n cube. Since electron is moving round the nucleus in a circular orbit, and because of that one some current is there, then magnetic field produced at the center is, magnetic field at center, formula is B is equal to mu naught I by 2R, which is In by Rn. This is going to be the Bn. So from this one, magnetic field of the nth orbit is proportional to the In by Rn. where In is proportional to the Z square by N cube, and Rn is, that is the radius of the nth orbit is N square by Z. So which is equal to the Z cube by N to the power of 5. Most important question you can get it. Suppose an electron is jumping from the first orbit to the second orbit, its magnetic field will be decreased by 2 to the power of 5, in the sense 32 times it decreases by. So remember that particular relationship, Nana, very important. And next, this is your magnetic field, Nana, B and A. And the next one is magnetic movement. Magnetic movement, where capital M is equal to I into area, that is current I into pi into radius r square. So In into Rn square. So that means which is proportional to the Z square by N cube and into Rn square, that is nothing but an N to the power of 4 by Z square. So Z square will be cancelled. So magnetic moment is proportional to the N. It does not have any sort of an impact of the Z in this particular relationship. So these are all the different relationships of the situation. Now coming down to the energy. So energy of electron, or the total energy of the electron in the Bohr's orbit, can be written as an En is equal to, actually it is e power 4 into mass by 8 epsilon naught square into h square of z square by n square. So this, by calculating all these information, this entire thing you will be getting it as an that is total energy is obviously the negative. So En is equal to minus 13.6 into z square by n square. So from that aspect, so and total energy of first orbit, these values should be remembered now. Of first orbit is equal to minus 13.6 electron volts. Second orbit is minus 3.40 electron volts, and the difference is 10.2 electron volts. That means if I want to send an electron from the ground state to the, that is first orbit to the second orbit, I have to supply 10.2 electron volts. Now third orbit, sir. Third orbit means n value you have to substitute as an the 3, z value will be 1, and you need to solve that one. So that is minus 1.51 electron volts. Next, you can substitute the 416, you'll be getting 0.92, you'll be getting somewhere around. So you just need to remember these values. So next one, as I have told you, excitation energies. Excitation energy from, excitation means from the first orbit to the second orbit, for example. From E1 to E2, that is first orbit to the second orbit, that is delta E can be written as an E2 minus E1, which is equal to the 10.2 electron volts. You need to substitute minus 3.4 minus of minus 13.6, you will be getting there. Now energy difference between any two levels. That is energy difference delta E, or you can take it as a E is equal to, delta E is equal to, that is h nu, which is equal to the hc by lambda is equal to minus 13.6 times of, this is 1 by n1 square minus 1 by N2 square for hydrogen. Hydrogen in the sense Z is equal to 1. For hydrogen like, so that is Hc by lambda, or your energy E is equal to minus 13.6 into Z square times of 1 by N1 square minus 1 by N2 square. This is for hydrogen like elements or hydrogen like atoms. Okay, sir. So now if I take this entire thing to the other side, that means Hc values and all these things. So you can write it as an 1 by lambda is equal to minus 13.6 into Z square by Hc of 1 by N1 square minus 1 by N2 square. On solving this one, this is being written as an 1 by lambda is equal to R times of 1 by N1 square minus 1 by N2 square, where R is called as a Rydberg's constant. Rydberg constant. The value of the Rydberg constant is actually 1.09, but you can take it as a 1.1 into 10 to the power of 7 per meter. Exact value కావాలి అంటే 1.097 into 10 to the power of 7. So any perfectionist, he can use that particular thing. Right, Nana? So this is the 1 by lambda relationship. From this one, we know that 1 by lambda is called as n is equal to nu bar, which is called as an wave number. దీన్ని wave number అంటారు. So from this one, wave number can also be written as an r times of 1 by n1 square by 1 by n2 square. So like this, please. So total energy will be always negative. Remember that particular point. Okay, so and the relation between the potential energy and kinetic energy also we have seen. Kinetic energy is equal to potential energy by 2, or potential energy is equal to 2 times of kinetic energy, and modulus of kinetic energy is equal to modulus of total energy. The only difference between the kinetic energy and the potential total energy is the negative sign of it, and both of them is equal to mod of z square e to the power of 4 into m by 8 epsilon naught square into h square of 1 by n1 square my 1 by n2 square. This is the modulus I am placing here. So this is only the relationship over there. Now there are the different series that we have. What are all those series, sir? So first one is called as a Lyman series. So Lyman series means from where to where you will be getting. So n1 I am writing here, n2 I am writing here. From n1 is equal to 1 to n2 2 comma 3 comma 4 so on. So this is the Lyman series, and in which region the Lyman series is going to be following. Lyman series falls in the ultraviolet region UV. The region and general formula is going to be the same thing. That is 1 by lambda is equal to R of, you will be substituting 1 by 1 square minus 1 by n square. Okay, so in this case, I'm also going for n. This is the formula. And the last one, I'm going for last two things. That is the longest wavelength. So for the longest wavelength, you have to go for n is equal to 1 to n is equal to n2 is equal to 2. Shortest wavelength from n1 is equal to 1 to n2 is equal to infinity, and the corresponding values are that will be the 1200 nearly, or 1215 angstroms. This will be the 912 angstroms. These values you have to better remember. So next type is going to be Lyman series. Tarvata. Next is a Balmer series. Balmer n value 2 and the transition from 3 comma 4 comma 5 etc. And this falls in the visible region. And the formula will be same thing, 1 by lambda is equal to, but only changes is 1 by 2 square minus 1 by n square. And here that in this case, as we know, n1 is equal to 2. And so n2 should be 3. And it falls in the region of so nearly sodium, that is 65,000 or 60 angstroms, this one. And here n1 is equal to 2 to n2 is equal to infinity 3946 angstroms. So this is the difference between the Balmer series and this one. Next one, Passion. In the Passion series, n value will be 3 and ranges from 4 comma 5 comma 6 so on. And this falls in an near infrared, that is near IR region. And the formula will be 1 by lambda is equal to R into 1 by 3 square minus 1 by n square. And whereas the longest wavelength for this one can be written as, and this is some 18,746. So longest can be obtained only from its orbit to the immediate next orbit. Shortest wavelength from its orbit to the infinity. This will be the 8,000 or this one 82,101 angstroms, right, sir? And the next one is called as your bracket. N value will be 4, transition from 5, 6, 7 like that, and this will be the middle infrared. Or if you cannot remember, just remember as an infrared, that's it. So this is 1 by lambda is equal to R into 1 by 4 square minus 1 by n square. And your longest wavelength will be the 40,000, nearly 40,500 angstroms too. It will be the 14,500 angstroms nearly. Next, after the bracket, P fund series. P fund వచ్చేటప్పటికి 5 is its base number, 6 comma 7 comma 8 so on. This is in the far infrared region. Formula will be 1 by lambda is equal to R times of 1 by 5 square minus 1 by n square. సో ఇంతవరకు మీకు గుర్తుపెట్టుకోవాల్సిన అవసరం లేదన్నా. మీరు అట్లీస్ట్ ప్యాషన్ సిరీస్ వరకు బామర్ వరకు గుర్తుపెట్టుకోవడానికి ట్రై చేయండి. ఏది లాంగెస్ట్ వేవ్ లెంగ్త్ అంతా షార్టెస్ట్ వేవ్ లెంగ్త్స్. ఇవన్నీ గుర్తుపెట్టుకోవాలి అంటే కష్టం. సో కొన్ని గుర్తుంటాయి, కొంతమందికి గుర్తుండవు. గుర్తుపెట్టుకోగలిగిన వాళ్ళు దే కెన్ మెయింటైన్ ఇట్. ఓకే సార్. సో దిస్ ఇస్ ద కండిషన్ సార్. Next one, so what are the basic things or other cases of this particular? So ఇవి మనకి మేజర్గా ఇందులో ఉపయోగపడేవి. దట్ ఈస్ ద రూదర్ఫోర్డ్స్ బోర్స్ మోడల్లో మనకి యూజ్ అయ్యి, రైట్ నానా. నెక్స్ట్ దాని దగ్గరకు వస్తే, సో ఇఫ్ అన్ ఫర్ ఎగ్జాంపుల్ if an alpha particle collides with an if an alpha particle is coming and or some neutron is colliding with an nucleus. So I suppose this is a neutron N01 is coming and colliding with an hydrogen like this H11 collision cases. So which is in the rest position initially, then what will happen? So suppose this hydrogen is absorbing this neutron. Then what sort of things it can be satisfied? Law of conservation of momentum, that is initial momentum is equal to the final momentum, that is the momentum of the neutron is equal to momentum of hydrogen. Okay, and it will also satisfy the law of conservation of energy. So initial energy, that is energy of the neutron, is equal to kinetic energy of the hydrogen plus Q. Q means energy released or absorbed conditions. And that is Q can be Q calculated by energy of the neutron minus kinetic energy of the hydrogen. This can be replaced with Pn square by 2 into mass of the neutron minus pH square by 2 into mass of the hydrogen. Now to calculate this one, if I take the common as Pn square by 2 into mass of the nitrogen. This will be the one, and as we know, neutron and hydrogen are same. So that means here we don't get it anything. So left over will be the mass of the neutron by mass of the hydrogen, which is Q factor. Q is equal to kinetic energy of the neutron into 1 minus mass of the neutron by mass of the hydrogen. And the same thing can also be equated to the kinetic energy of the hydrogen is equal to 1 minus mass of the hydrogen by mass of the neutron. So this can be used in the different circumstances, Sandy. Now let's see this particular things, please. Here, one of the some the wavelength of the first spectral line of the sodium. So he has given the sodium wavelength. The first excitation he is asking, excitation potential he is asking. So lambda minimum is equal to what is the, or will we go for the general formula? G is equal to Hc by lambda, which is equal to the potential into charge. From this one, lambda can be written as an Hc by EV. H value is 6.63 into 10 to the power of minus 34. C into 10 to the power of 8. Charge of an electron 1.6 into 10 to the power of minus 19 into wavelength, or he needs the wavelength over here. Here V is the potential. So now remember, take the potential onto this side, which is 6.63 into 10 to the power of minus 34 into 3 into 10 to the power of 8 by 1.6 into 10 to the power of minus 19 into wavelength 5896. You can take approximately 6000 and go ahead for that one, sir. Into how many times? Angstroms 10 to the power of minus 10. I'm just directly going for an approximation here. This is 6000. This will goes up. This approximately goes for 5 times. 1 by 5 nearly your answer should be 2.1 electron, 2.1 volts. Because it is coming out almost 1 by 5 on that range. 1 by 5 will be 0.2. Adjusting the powers, you will be getting obviously. Next one, an electron collides with the hydrogen atom in the ground state, excites to energy equal to 3. The energy given by the hydrogen atom in this inelastic collision is purely giving an inelastic collision energy release. So as we know, energy released is equal to 13.6 into 1 by n1 square minus 1 by n2 square. Now this is equal to the 13.6 in terms of electron volts only. This is excited ground state means 1 by 1 square minus 1 by 3 square. That is 1 minus, we can write it as an 13.69 minus 1, 8 by 9. So on solving this one, we should be getting somewhere around 12 around, we should be getting this one. So most probably it should be the 12.1 electron volts. You can go for the multiplication, cross check. Next one, the energy of the highest energy photon of the Balmer series nano in an hydrogen spectrum. Just now we have written, sir. So what is an highest energy of the photon? Highest energy means wavelength should be the lowest one. So that means energy E is equal to, how you can write it as an Hc by lambda. So what is the wavelength in the Balmer series for the shortest wavelength is which is 12400. I'm going approximately by lambda for the shortest wavelength in the Balmer series is nearly actually 3950. It will be coming down or solid with the 4000. Nearby answer we can get it now. 12400 by 4000. This one. These two will goes off. 124 by 40 in the sense it should be some 3 point something. The only option there in this one 3.4. Electron volts, right, sir? Next one. Ionization potential means what do you mean by ionization? You need to send an electron which is in the ground state to out of the all the shells. That is removed from the influence of the nucleus. So ionization potential of the hydrogen is 13.6. Hydrogen atoms in the ground state are excited by monochromatic radiation of energy. So energy also he has given. According to the Bohr's theory, the spectral lines, number of spectral lines he is asking. So ionization energy he has given it as a 13.6 electron volts. There is definitely an excitation from which energy 13.6 to it is going to the 12.1 means the energy difference is 1.5 electron volts energy, and this energy is equal to the ionization energy by n square. That is 13.6 by n square only కదా ఇది. Energy E is equal to 13.6 into z square by n square. Since here it z is hydrogen only, z value 1 అంటే ఇదే కదా నాన్న. దీన్ని సాల్వ్ చేసుకుంటే ఎంత వస్తుంది ఇప్పుడు? Sorry, 1.5 is equal to 13.6 by n square. From this one, n square is equal to 13.6 by 1.5. And 0.5, 13.6, 135 అయితే 9 అవుతుంది నాన్న. So almost equal కాబట్టి I'm just going for this one as a 9. So nearby value, so n should be equal to the 3. So lines emitted is going to be this one. Next one, please. An alpha particle of the energy half mv square bombards with a heavy nucleus target of the Z square. Then he is asking the closest distance. First topic today we have discussed. So what is your closest distance is? That is you can solve it as an mv square by r is equal to 1 by 4 pi epsilon naught into Z square by r square. 4 Z square by r square. Remove this one or closest distance. R is equal to kinetic energy is equal to potential energy రాసుకున్న problem లేదు. Z square by mv square. So R is inversely proportional to the mass, inversely proportional to the velocity square, and directly proportional to the ZE square. So ఇందులో మనకు వచ్చేది second option మాత్రమే. Okay, sir. Now coming down to your next topic of today's, I'll go for the nuclei, please. What do you mean by nuclei here, please? A nucleus is or it is a centrally concentrated structure for an atom where the protons and the neutrons will be located. Okay, now. So from this one, the basic set చేసుకుంటూ వెళ్తున్నానా? So any element can be written as an by its mass number and atomic number Z, and this one is going to be the A. Okay, so this is the general conditions, and generally the total number of the protons will be equal to the total number of neutrons ఇలా ఉంటాయి నాన్న. సో దాని ప్రకారం తీసుకుంటే there are the different things. What do you mean by isotopes? Isotopes are those elements same atomic number, same A, but different Z. But different Z value. So element having the same atomic, same Z value, but different A value. Mass number will be different. Examples, you can have a lot of examples, that is H11, H12, like this, H13. Anything you can go for like this. Next type of the topics are Isobars. What are your isobars means? Same mass number but different. That is same A, different Z. Next one, isotones. What are your isotones means? Same number of neutrons. Next one, isomers. What are these isomers? Atoms of same number of atoms of same number of protons and neutrons. But energy states are going to be the different. But different energy states. Different energy states. Okay, na? So you can have both of them uranium 23492 as రెండు ఒకలాగా. So ఒకటేమో excite అవుతుంది, ఒకటేమో excite అవ్వదు అందుకనే. Now coming to the sizes of this one. So volume of nucleus, that is V, is proportional to the mass number A, in the sense 4 by 3 pi R cube is proportional to the A నే కదా, దీనిలోంచి R cube is equal to 3A by 4 pi. So this is your R cube conditions. From this one I can write the R is equal to 3A by 4 pi whole to the power of 1 by 3. And from this one R is equal to R naught into A to the power of 1 by 3 అంటే R naught వాల్యూ ఎంత అవుతుందని ఇప్పుడు దీని నుంచి 3 by pi ఏగా ఇది కిందది 3 by 4 pi value, you'll be getting something like this. Or this is your general formula of the radius of nucleus. Radius of nucleus. Where R naught value ఎంత రాసుకోవచ్చున్నాను ఇక్కడ మనం R naught is equal to 1.1 into 10 to the power of minus 15 meters or 1.1 Fermi. Okay, Nana. Next one, in this case, nuclear density will be almost constant. Nuclear density will be almost, this is constant case. Okay, now 1 AMU means what? 1 atomic mass unit. One atomic mass unit, 1 AMU is equal to how many times? Which is equal to the 1/12 of the mass of the carbon isotope. And the value can be written as an 1.67 into 10 to the power of minus 27 kgs. 1 AMU value, please. Right, Nana? So in the same case, mass of the proton can be written as an mass of the proton 1.007275 AMU. Similarly, mass of the electron is equal to 0.00, and another one like this is going to be the 55 AMU, that is almost equal to the 0.51 million electron volts. And the last one is mass of the neutron. Mass of the neutron is 1.008665. So this is your mass of the neutron conditions, please, and all of them. Okay, so then now coming to the nuclear forces. Nuclear forces. What are these nuclear forces basically? There are the different types of the nuclear forces. Here they are the attractive in nature. Okay, so they exchange the mesons on all these things. And you remember this basic relation 2 years back in the mains examination also he has asked relation between the gravitational force, electromagnetic force and the nuclear force. That is 1 is to 10 to the power of 36 is to 10 to the power of 38 between an proton and proton conditions. And you can also say that forces between neutron, proton, and proton neutron is of same value. Is of same value. Okay, no. So like this, these are the different situations where the forces relation direct గానే అడిగాడు ఇంతకు ముందర జాగ్రత్త. Next, I'll go for the mass defect, sir. What is this mass defect is basically? So it is the difference between the calculated mass and the actual mass. Calculated mass and actual mass. So what do you mean by calculated mass? That is delta m is equal to z into mass of the protons plus a minus z into mass of neutrons minus this is your actual mass is here. So this gives you the mass defect. And the next one, packing fraction. Packing fraction can be written as an it is delta m by a. Nothing but packing fraction will be the value of the packing fraction is high. That means that nucleus is more stable. Okay, sir, that is the main major thing. So stability of the nucleus, if this is high, obviously the nucleus is also stable. Next one, binding energy. Binding energy is equal to delta m into c square. That is mass defect into whatever the mass is there, that will be converted into the binding energy. This is in terms of the joules. Or the same thing can be written as a delta m into 931.5 million electron volts. So this is the binding energy conditions. And binding energy per nucleon, binding energy per nucleon, that means which is equal to the BE by A, which gives the stability. So the ratio binding energy per nucleon by ratio will explain the stability of the nucleus. Suppose if you plot a graph between the BE by A and A, where BE by A is on the y-axis and this one is on the x-axis. The shape of the graph will be coming out like this. Okay, sir, like this, the graph will be there generally. So the elements which are far away are also not stable. The elements which are less than 28. Then the elements which of them are going to be the stable thing. In this one, the maximum binding energy per nucleon value is equal to maximum binding energy per nucleon value is 8.8 million electron volts, and that will be remained with the iron. That is Fe దగ్గర ఉంటుంది నాన్న maximum value ఇది and minimum value deuteron you can have it as a 1.4. Okay, so the elements which are within the range of that is 28 less than or equal to A, this one is less than or equal to the some 156. ఈ range లో ఉన్నవన్నీ కూడా they are stable. They are all these elements will be in terms of the stable లోనే ఉంటాయి. సో మరి స్టెబిలిటీకి రావడానికి ఏం చేస్తాయి న్యూక్లియసెస్ ఇవి? దే అండర్గో, దట్ ఈస్ స్మాలర్ న్యూక్లియై undergoes, okay, the smaller nucleus undergoes fission reaction, and larger nucleus undergo fission. Right, Anna? So fission and fusion are responsible for the దేనికోసం అన్న అవి మనకి అంటే for acquiring the stability. So on losing them, they acquire the stability conditions. Right, sir? So ఇంకా ఇందులో మనకి మేజర్ గా ఉండేది రేడియో యాక్టివిటీ నాన్న. రేడియో యాక్టివిటీ ఫార్ములా ఏంటి? ఆల్ఫా పార్టికల్స్ బీటా పార్టికల్ డీకే కదా. నెంబర్ ఆఫ్ పార్టికల్స్ decayed is equal to initial number into e to the power of minus lambda into t. Okay, now you go to next one where lambda is called as a decay constant. Decay constant, that is dn by dt is equal to lambda into n. Generally this will happen, and solving this relationship you will be getting this n is equal to n naught into e to the power of minus lambda t. రైట్ అన్న? సో దీన్ని సాల్వ్ చేసుకుంటే మనకి ఇది వస్తుంది. ఇందులోంచి కొన్ని రేడియో యాక్టివిటీ కూడా, దట్ ఈస్ యాక్టివిటీ ఏ ఈజ్ ఈక్వల్ టు ఏ నాట్ ఇంటూ ఈ టు ద పవర్ ఆఫ్ మైనస్ లాంబ్డా టీ. అండ్ టీ హాఫ్ అంటే టీ హాఫ్ ప్లీజ్. సో వాట్ ఈస్ ద టీ హాఫ్ దగ్గర ఏం జరుగుతుంది నాన్న? ద డిసింటిగ్రేటెడ్ మెటీరియల్ బికమ్స్ హాఫే కదా. Disintegrated of nuclei, okay, na, to half. That is this mass is reduced to half, and the T half formula is equal to 0.693 by lambda, which is equal to the ln of 2 by lambda. It is your T half, and mean lifetime tau is equal to 1 by T half nana. Oh sorry, 0.693 by T half, which is also equal to the 1 by lambda. ఓకేనా? సో మిగతావి చాలా మటుకు ఇందులో థియరిటికల్ క్వశ్చన్స్ ఎక్కువగా వస్తాయి. మోస్ట్ ఆఫ్ ద క్వశ్చన్స్ ఆర్ ద థియరిటికల్ బేస్డ్ క్వశ్చన్స్ దే విల్ బి ఆస్కింగ్. సో ప్లీజ్ బి కేర్ఫుల్ ఆఫ్ దిస్ వన్. అండ్ పవర్ ఆఫ్ ఏ న్యూక్లియర్ రియాక్టర్ ఈస్ power of a reactor P is equal to number of fission reactions into energy by time. So these are your major important questions in this particular nuclear physics, nuclear thing. So now coming to this one, sums. Consider an initially pure 3.4 grams of the sample of gallium 67 and isotope that has a half-life of 78 hours. What is an initial decay rate, he is asking. What is the mass of the gallium, sir? Here given mass is, that is mass of Ga is equal to 3.4 grams. That means minus 3 kgs. So and he has given T half, that is the half-life period also 78 hours. Half-life also 78 hours, sir. So from this one we know that T half is equal to, just I have written, that is ln of 2 by lambda. From this one decay constant lambda is equal to ln of 2 by T half. ln of 2 in the sense 0.693 by T half is how much? 78. Now what will happen if you solve this one? Okay, this will be the somewhere around 8.89 into 10 to the power of minus 3. So that means how many number of reactions have been participating? Number of atoms, which is equal to the M into Na by, that is Avogadro number by molecular weight, which is 3.4 into 6.023 into 10 to the power of 23 by molecular weight of this one is going to be how much? That is 67 you can do. So next initial rate of the decay is equal to, that is dN by dt, which is equal to the lambda into n naught thing. So lambda into n naught, and the lambda value is going to be 8.89 into 10 to the power of 5 into 10 to the power of, sorry, minus 3, 8.89 into 3.056. The next one into 10 to the power of, we have got this value, sir. 10 to the power of 22 here. Okay, this is on solving this one. 8 threes, this is the one. Okay, that is one. Okay, 7.53 into 10 to the power of 16 per second. And at t is equal to, you need to calculate for 48 hours. So now substitute in the activity formula, R is equal to R naught into e to the power of minus lambda into t by minus lambda into t only. Now put down values, sir. This is 7.53 into 10 to the power of 16 e power on solving lambda into t 0.427. Now on solving this one, you'll be getting it as an 4.9 into 10 to the power of this one per second. So this much, it's a heavy sum, which if it comes in the Eamcet, you can leave it, sir. Next, half-life of the uranium is in this much he has given. Rock contains 60% of the original uranium. He is asking age of the rock. That is N is equal to N naught into e to the power of minus lambda t, in the sense N by N naught is equal to how much? N by N naught is equal to 60 by 100 is equal to how much? 1 by 2 power n. From this one, 2 power n is equal to 10 by 6. Now apply the log on either side. Applying log. So how much you will be getting, sir, here? On solving, n into ln of 2 is equal to ln of 10 minus, this is ln of 6. So or else you can directly multiply with the 0.693. That's also can be possible, sir. So but you need to just substitute these values. Log 2, log 6, log 10, all these values you need to apply. Then you will be getting the time t is equal to n times of t half, which is equal to the 0.74 into t half is 4.4 into 10 to the power of 8, which is equal to the 3.3 into 10 to the power of 8. This is the condition, sir. Next, Nana. A radioactive substance is reduced 1 by 16th of its original mass in 40 days. 1 by 16th అంటే ఎన్ని ఎన్నిరా 2 to the power of 4 రాసుకోవచ్చా అంటే 4 half lives 40 days. Then what is the each half life ఎంత అవుతుంది? Okay. Shall we apply this relation? N is equal to n naught into e to the power of minus lambda t. From this one, n by n naught is equal to 1 by 16, which is equal to the e to the power of minus 0.9, that is 693 log n value in n into 40 by t half value. So now again apply the log and solve it. You will be getting the t half is equal to 10 days. Right, sir? Next question, please. That is mass spectroscopy. Okay, it's a previous mains question, but it's a lengthy process. So the same thing you need to apply the relations, that is mass of the number of Potassium is equal to N naught into e to the power of minus lambda T. Similarly, number of argon is also equal to the N naught into e to the power of minus lambda into T. So on solving this one, you can get the value of the T is equal to how much? Right, so it's a lengthy case. Basically, when a proton and an anti-neutron annihilate, energy released ఎంత అవుతుంది? That will be your first option. దీన్ని ఎలా చెప్పొచ్చు sir? Energy released can be written as an mc square. So mass is going to be the two protons. Mass is same 1.6 into 10 to the power of minus 27 into this is a c square. C square means 3 into 10 to the power of 8 whole square. On solving this one, you'll be getting it as an 4 point, sorry, it should be the 2.88, right, sir? 916, 2.88 into 10 to the power of minus 10 joules. So this is the readjustment of this one. You can have this, please. Energy released in this annihilation. Or what do you mean by annihilation means? Two objects are combining is called as your annihilation. Or we separate, I think. Okay, they are called as an uh, that means they are merging on code shoe, they are combining. Okay, so these are the different things here, please. So hope you have got this one, please, and you can start your quiz program for the today. Okay, now. Thank you, sir. Thank you, everyone.